welcome to our hand computation of a two-way between subjects ANOVA. Here I have some data for you, but unlike previous videos, I'm going to have to remove the data for most of the time that we'll be doing computations together. So if you find that having the data in front of you might be helpful, then feel free to copy that down now by hand if you want, or if it's possible to take a screenshot of this slide, then please do so, just so that there isn't any sense of disorientation because we don't have the raw data to refer to right away. Now, this data may look partly familiar. So this chunk on the left is the data that we worked with when we computed our one-way between subjects ANOVA. And we decided to see whether or not there was a significant difference among the groups. We have our means here from before, and we have our standard deviations, which we actually calculated together by hand. Now there's introduced some new data. So this data, it still has the same group 1, group 2, and group 3. But the way that we're going to view this is that a whole other group of participants, 15 of them, were recruited so that they would be randomly assigned to group 1, group 2, and group 3 and respond for our dependent variable, but at night. So I've introduced another factor or a way so that it can be a two-way ANOVA, and we're interpreting it as between subjects in that there are 30 different subjects now that are making up our full data set, 15 provided responses during the day, and another 15 provided responses during the night. So our big N is 30, and that's definitely 30 observations, as you can see by counting the observations in the chart. But it's also 30 subjects. It is shorthand for subjects, and it's little s's because big s's, when placed together, look like sums of squares. So, you know, I mean, it's just a mess. That's notation for you. So back to our data. Because we have these new observations here, we'd never computed a mean before, standard deviation before, for group 1, group 2, and group 3 during the nighttime. So I am a nice person and I've provided those means for you. So group 1's mean is 2.2. And wow, that happens, you know, you say stuff and then you write a different stuff. Yes, 2.2. And then the standard deviation is 0.447. It's going to be an interesting day. Okay, so then group 2's mean also happens to be 2.2. And its standard deviation is 1.643, so a bit higher than group 1's. And finally, group 3, okay, spoiler alert, is 2.2 for the mean and 0.837 for the standard deviation. In fact, the standard deviation is coincidentally related to these two as well. So we have our between subjects data, and it's a two-way because we have two factors. The first factor is group with 3 levels, and the second factor is the timing, or the time. And the 2 levels for that factor are day and night. All right, so forgetting about the actual data for a second, let's think about what it is we need to compute in order to get the results from our two-way between subjects ANOVA. Well, because there's 2 factors, group and timing, both between subjects, we're going to get an F-test for the effect of group. Is there a difference between group 1, group 2, and group 3? Yes or no? And then we're also going to get an F-test for the effect of timing. So is there an effect of having participants respond during the day versus when others respond at night? And finally, this confusing fellow, which is the group by time interaction, but I shorthanded group to GUP because I didn't want a very long subscript. So these are the 3 F's that we're going to get. Interactions, they are confusing. They take some time to understand, and typically one would understand a little bit about an interaction and then learn some more stats and some more psychology and then understand a little bit more. The F test for the group is the mean squared for the group over the mean squared error. Okay, also known as MS capital E in at least APA symbolism, but I like to put the subscript, as you know. Okay, then for our day versus night manipulation, we have the mean squared for the timing, or time I'll call it, divided again by this mean squared error term, and it's the same one. So we only need to compute it once. And for the interaction, a mean squared of the group by time will also be computed. So first off, we need the sum of squares for the group, just like we needed it for the one-way ANOVA. So since we've introduced our new factor timing, we'll also need a sum of squares computation for that factor. Then, once we have the degrees of freedom for each of these, we'll be able to find our mean squared group and mean squared time respectively. But we also need a couple other sums of squares now. We need something called SS cells, sum of squares cells. And that's since we have a formula, SS cells, is going to be able to help us get our sums of squares for the group by time interaction by subtracting SS group and then subtracting SS time once we have them. And then, let's see, that will be equal to the sum of squares group by time. Okay, last but not least, so we needed this, we needed this, we needed this, and that was going to give us this interaction sum of squares. And finally, we also need SS total. And that's because SS total can be used similarly to SS cells to help us find something that we actually want. SS total minus SS cells is equal to SS error. So we want SS group, SS time, we want SS group by time, and SS error. And some of the more simple ways to compute sums of squares are to compute a different type of sum of squares and then subtract off other ones through an understanding of what these represent and why we get what we get when we do the subtraction. So what I'm going to do is I'm going to try to explain why it is that SS cells, like what it is and how it's going to help us. So before, when we did one-way ANOVA, we had SS group. This is just my rough drawing here. Oh, sorry, I should say MS group, right? Because like I'm making an F ratio. And MS error. So we needed the sums of squares group, and that was all the between groups variance. That was what MS group captured once we divided by degrees of freedom. But now, because we have more than one factor, there's this kind of sum of squares that you can compute. And the way I like to look at it is almost as if it's like a super sum of squares group. It's kind of like the sum of squares that explains all the possible variance due to the fact that we have a group variable and a time variable. Okay, welcome back. So before we compute all of the yummy sums of squares, we are going to need our marginal means and our grand mean. The reason that what we're about to compute are called marginal means is because they're written in the margin of kind of like a cell mean table. So since we have 3 groups and we have 2 levels of timing, we have 6 cells, 1, 2, 3, 4, 5, 6. And what I've done is I've put just the mean, not worried about the variance, standard deviation type measurement right now, into each one. So group 2's mean for the day is 3.2, as you might recall, but then for the night it becomes 2.2, like the rest of the nighttime means. And here is also the cell size. So, because the n's are equal across all of these cells, I can use my shortcut where the cell means that are written here can help me to find the marginal means. So can you do the group marginal means for group 1, group 2, and group 3? Why don't you maybe give a pause and then come back and see if we got the right answer. So I can't pause your life, so I'm just going to continue. You can compute the mean of these two means and get the grand mean, or you can compute the mean of these three means, divide by 3 when you're doing that, and you would get the grand mean. So why don't you give that a try and see what you get. Cool. I'm assuming you're back or have never left. So 4 plus 2.2, 6.2 divided by 2 is 3.1. Don't worry, I've done this calculation before. That's why I'm fast with it. And then here, if we add 2, 2.7, 4.6, and divide by 3, you'll also get 3.1. Ladies and gentlemen and friends beyond the binary, I have made a typo. Here is a kind of schematic of the cell table that was showing not too long ago, and what I was doing was I was kind of emphasizing how many observations had made our marginal means. These row marginal means indicated the marginal means for the day and the night. And then these ones in the columns indicated the marginal means for group 1, group 2, and group 3. But this doesn't make any sense to have 15 observations representing each of the 3 groups and at the same time 15 representing each of the 2 times. As a matter of fact, there's only 10 observations that are contributing to the marginal means for group 1, group 2, and group 3. So if you have any questions about that, you can let us know. I'm kind of glad that that came up. It's what everybody says when they made a mistake. I did it to teach a point. No, that was a total mistake, but I'm glad it came up so that we could make sure that if you don't understand why it is I made a correction or any other issue, then you can definitely speak to us. All right, so without further delay, we're going to start with our SS group. So SS group can be written as 10 times 2 minus 3.1 squared plus 2.7 minus 3.1 squared plus 4.6 minus 3.1 squared. Okay, so the reason that it looks like this is because there's 10 observations in each cell, so to speak, that contribute to each of these 3 terms. Okay. So because SS group is ignoring the manipulation of time, then if you examine our new data, you'll see there are 10 observations that contribute to the marginal mean of 2 for group 1, 2.7 for group 2, and 4.6 for group 3. So then this 10 out here multiplies by each of these terms in order to kind of weight the variance according to how many observations there were. If we had more observations, this number would go up. Perfect. And now we're going to compute SS time in a similar way. SS time is equal to 15 times the following sum of squares. for marginal mean for daytime minus grand mean 3.1 squared plus, that's not right. Why does it say 15? Like who's in charge here? This is 2.2. This is the land of typos. All right, so then we have 2.2, which is the marginal mean for the nighttime minus the grand mean. We square those, and for each of those, because day had a chunk of 15 data points in it, and night also had a chunk of 15 data points in it, we're multiplying by 15 out front to properly weight this time variance quantity. Excellent. So now we are going to want to find our sum of squares for the group by time interaction. And remember, we talked about how we can do this by subtracting some other sums of squares that we've already computed. So SS group or group times time, to save some space, is equal to this SS cells minus SS group, which we found and it's listed here, minus SS time, which we found and it's listed here. To compute SS cells together without the data in front of us, we'll either rely on the data that you've written down or have as a screenshot, or we're going to rely on memory. So we have SS cells. We have to compute that by hand. So what we're going to do is very similarly to how we computed SS group and SS time, we're going to pull up the cell size as the multiplier here. And then we're going to go and we're going to recall those cell means. So the first one was 1.8. That was just one cell mean of the 6. And we're going to subtract 3.1, the grand mean, from that. And then the next cell mean we could recall is 3.2 minus 3.1. And then we're going to add some more. We had a 7, our big mean from the daytime folks. And then remember how we had all 2.2s? So I'm going to take my shortcut and I'm going to compute 2.2 minus 3.1 here. I'm going to square that, and then I'm just going to multiply it by 3 because I don't feel like writing 2.2 minus 3.1 squared plus that again plus that again. So if that works for you, you can do it too. And to clarify, so because we're looking at these terms, there are actually 6 terms here. 6, 1 for each of the cell means. So we have 1, 2, 3, 4, 5, 6 terms. They just written like 4. So this is n equals 5 per cell, because each of these terms is represented by a mean that had 5 observations contributing to it. That's why the 5 goes there. And this is kind of like, say we look at this term. This is a measurement of how the cell mean differs from the grand mean. More technical kind of way of understanding it. And we have 6 cells, so that equals 6 of those sums of, or squares, square terms that we are summing. Okay, so I hope that makes some sense. Keep up the good work. We're going to compute that now. Okay, are you ready? We have our SS group times time, or our interaction sum of squares, equal to SS cells minus SS group minus SS time. We don't want a negative number here. That might indicate that I had made a mistake. Okay, so we end up getting 36.2, which is kind of unnerving because cells, sum of squares group rather, is 36.2. That's okay. Sometimes the numbers just work out to be similar. We had that happen last time when we did linear contrasts, and our 2 contrasts gave us really eerily similar sums of squares. It happens with fake data a lot, I'm sure. But that's great. We have our interaction sum of squares and we did not make an error. It just happens to be the same number as the group variance. Next up, we're going to compute SS total. you've seen SS total being computed before. As long as we understand that the total sums of squares is always created by taking every observation, subtracting the grand mean and squaring that, then adding all those up, no multipliers because it's every observation that goes into here. So we'll have 30 terms, then you understand enough. But you may want to wish me luck. All right, we have our total sum of squares, a whopping 206.7 whatever variance units. And so we can compute SS error. That's given to us by familiar formula that we take the total variance, subtract off the variance that's due to the fact that we have manipulation, so a between subject variance total, and we're left with the within subject variance total, which is our SS error. Another way to think about this is we took SS total and subtracted, like if you could see the way that this formula breaks up, SSLs is composed of SS group, SS time, and the interaction term. So SSLs is just representing all the variance due to group, time, and the interaction. Subtract that away from total, and all you've got is within subject error. Okay, I have explained it long enough. That is equal to 206.7 for SS total minus SS cells, which is 96.7 written in the margin here for us, and that gives me 110 even. We want to compute the mean squared error. So our mean squared error, which will go on the denominator for all three of our F tests, is sum of squared error divided by the degrees of freedom error. Okay. How do we do that this time? Well, we know that 110 is the sum of squares error, okay? And the way that you can think about the degrees of freedom error is it's going to be the number of cells times the number of observations per cell minus 1. So that's one way that you can write a formula for it. So that's going to be 110 divided by 6 cells times 5 minus 1 per cell, so 6 times 4, similar to how we logicked out MS error for the one-way, and that's 110 divided by 24, and that is equal to 4.583. Okay, we are getting really close here, so now we're going to compute the mean squared group and mean squared time. So we have numerators for our group F test and our time F test. And so what that is for group, it's just the sum of squares divided by the corresponding degrees of freedom. So that's 36.2 looking over here. And when we compute degrees of freedom, it is the number of groups minus 1, or groups minus 1, because I've given up on writing the word group. And when you compute that, you get 18.1. That's a familiar number from before, so is the 36.2. Try not to worry about that too much. That's actually not a concern or too much of an interest for us. And let's compute the mean squared time. Why don't you pause it and go ahead and try. And I'll just keep going. So the sum of squares time is 24.3. And we're dividing that by degrees of freedom for the time. There's only 2 times, day and night. So we're going to get just a 1 here, 2 minus 1. So that's just going to give us 24.3 divided by 1, which is 4.3. So now we have our mean squared group and our mean squared time. Last but not least, we're going to compute the interaction. The pattern is that is the sum of squares of the interaction divided by the associated degrees of freedom. And so if we look here, we can find that that numerator is 36.2. We already computed it using our SS cells and so on. And then we're going to divide by the degrees of freedom for group times the degrees of freedom for time, whenever you have an interaction of two factors here and you want to compute the degrees of freedom so you can find your MS or you can report or something, it's always just degrees of freedom of the first one times degrees of freedom of the second one. So that's 36.2 divided by 2 for degrees of freedom group times 1 for degrees of freedom time, and that gave us an 18.1. All right, friends, we're gonna have to hurry up the cakes here because I am running out of whiteboard ink. But happily, we're almost done, so that worked out quite nicely. So we have our 3 F tests because we had 2 factors, and then because we had more than one factor, the 2 may interact. Okay, I wrote on my desk because I'm dedicated to your education. So look, see, now we can just pause for a moment and we can take a look at how we were able to get to our 3F values. This one is almost surely significant just because usually I don't worry if the F is, you know, around 5 or higher. It's usually when they hover around 3 or 4 that you kind of want to check. I'm not going to. But stick around and I'll show you how you can report just those F statistics in our APA format. So this first F here is F at 2 and 24 degrees of freedom, which is 3.95. An F table is needed to determine significance since we did this by hand. This is a test of the main effect of group. So was there a difference between group 1, group 2, and group 3, ignoring the effect of time, or as we say, collapsing across time? Here we have F at 1 and 24 degrees of freedom for the main effect of time, and it was 5.30 rounded. I'm pretty sure, again, as I had mentioned, that that's significant, but if it's not, somebody, you gotta correct me, and I'll make another I'm sorry video for you. And then finally we have our interaction effect. So that's F at 2 and 24 degrees of freedom, that's 3.95. We had a lot of similar numbers working through the calculations between group and group by time, so we ended up getting the same thing. Does not have to happen. These two need not be equal. It just happened because I invented the data and I tried to make it friendly in other ways, so sometimes that happens then. Now, let's focus in on what it means to have that interaction there. 3.95, that's a pretty good F. Not sure if it's significant, but for our purposes, just understanding what's going on with the data and why, if this was significant, it would be of interest. So our day data, which was what we used to do our one-way ANOVA last time, is kind of like if you start with group 1, then group 2, and group 3, and the DV is on the y-axis. Well, group 1 had a mean of like 1.8 or something, and then like group 2 was like 3.2, and like group 3 was 7. So they kind of like have an upward trend. If you decide that group 1, 2, and 3 should be shown in this order, of course. But if you show group 1, 2, and 3 in the same order for the nighttime, and you look at our DV, then you know that 2.2 is like somewhere in between the 1.8 and the 3.2, so I'll just put it here. But it didn't change. So despite there being 3 levels of group, at night there was no effective group, but in the day there certainly seems to be. So I thought that that might help illustrate. So an interaction is when you look at levels of, in our case, our time factor, and you see that the groups are having kind of this different collective effect in each of those levels of timing.